Welcome to lesson 1 of 1 in this tutorial, covering oxidation, reduction and redox equations. This is our only lesson in the topic of redox. In the last lesson, we covered the equilibrium constant and calculated a value for it using equilibrium calculations. Here are the key learning objectives for this lesson. First, we will look at oxidation and reduction. Then, we will look at redox reactions. Here are the AQA specification points for this lesson. Feel free to pause the video now and read through them before we begin. First, we will cover the terms oxidation and reduction. Here are some key terms we will cover in today's lesson. The first are oxidation and reduction. Then, we will look at redox, oxidizing and reducing. An oxidation reaction is the process of electron loss. And oxidizing agents are electron acceptors. A reduction reaction is the process of electron gain. And reducing agents are electron donors. Remember the abbreviation oil rig to learn how electrons are gained and lost. Oxidation is the loss of electrons, whilst reduction is the gain. A redox reaction is when both oxidation and reduction are happening at the same time. Here, we can see the reaction between potassium and chlorine. This is a redox reaction. Here, we can see that the potassium has undergone oxidation, whilst the chlorine has undergone reduction. An oxidizing agent gets reduced by accepting electrons. A reducing agent will get oxidized as it gives up electrons. The oxidation state of an element represents the total number of electrons that the element has either accepted or donated to get to its current form. If an element undergoes oxidation, then it will increase in oxidation state. If it undergoes reduction, then it will decrease in oxidation state. In this reaction, the potassium has lost an electron to form a positive K+ ion. Its oxidation number will have increased by 1, whilst the chlorine gained an electron to form a negative Cl- ion. Its oxidation number decreased by 1. Let's look at another example together. Iron forms a number of different ions, for example, Fe2+ and Fe3+. If you think about how these might be produced from iron metal, the 2+ ion will be formed by oxidizing the metal and removing 2 of the electrons, leaving us with an Fe2+ ion. The ion is now said to be in oxidation state of +2. However, if we remove another electron, this will give us the Fe3+ ion. Now, we will look at how we assign oxidation states. You should be aware of the 8 main rules for assigning oxidation states of an element in a compound or ion from the formula. First, the oxidation state of an uncombined element will be 0. This is because it hasn't been oxidized or reduced yet. The sum of the oxidation states of all the atoms or ions in a neutral compound will also be 0. For example, sodium chloride has an overall oxidation state of 0. Next, the sum of the oxidation states of all the atoms in a simple monatomic ion is equal to the charge on the ion. The K+ ion has an oxidation state of +1. The overall oxidation state in a compound ions is the overall ion charge. The overall oxidation state of NO3- is -1. This is the nitrate ion. Our fifth rule is that elements exist as identical atoms bonded together have an oxidation state of 0. For example, oxygen and chlorine have an oxidation state of 0. Next, we need to know that a more electronegative element in a substance is given a negative oxidation state. The less electronegative one is given a positive oxidation state. It's useful for you to know that fluorine is the most electronegative element, followed by oxygen. Some elements almost always have the same oxidation states in their compounds. We can see a table of these here. For example, group 2 metals will always have a normal oxidation state of +2. Our final rule is that Roman numerals can also represent oxidation states in chemical names. An example involving iron is shown here. Here's a useful summary of our 8 rules. Feel free to pause the video now and take a quick note of them for your revision before we move on. Our next specification point is to work out the oxidation state of an element in a compound or ion. This is an ion in question 1, so the sum of the oxidation states is equal to the charge on the ion. There is a shortcut for working out oxidation states in complex ions like this, where the metal atom is surrounded by electrically neutral molecules like water or ammonia. The sum of the oxidation states in the attached neutral molecule must be 0. This means you can ignore them when you do the sum. This means that the compound we've been given here is an unattached chromium ion, Cr3+. This means its oxidation state will be +3. Pause the video now to attempt the rest of the questions on your own before we reveal the answer. The answer for question 2 is +5, whilst the answer for question 3 is +3. Again, pause the video now to attempt these questions on your own before we reveal the answers. The answer for question 4 is +5. Question 5's answer is +6, and the answer to question 6 is +1. Our final point here is to learn how to combine half equations. You should be able to form an overall redox equation by combining 2 half equations. A half equation will tell you whether reduction or oxidation has taken place. For example, if electrons have been lost or gained from the elements involved. Let's go through a method to form redox equations. First of all, write the 2 half equations for the reduction and oxidation reactions that take place. Next, ensure that both the half equations contain the same number of electrons. Finally, we can combine the half equations to make a full redox equation. Remember to cancel out the electrons on either side, as they will be the same on both sides. Let's attempt this practice question together to apply the rules we have just learnt. Pause the video now to try it on your own. Here's the answer. We'll go through it together step by step. First, we need to write out the two equations for reduction and oxidation. Here, we've got one for chlorine and one for iron. The chlorine has been reduced, whilst the iron has been oxidised. Now, we need to make sure that both the equations have the same number of electrons, so we will balance them out here. As shown, we've included a 2 in front of the iron equations to balance the electrons. Now, we can put the two equations together and cancel out the electrons on either side, leaving us with our final answer as shown here. We've now covered all the learning objectives for today's lesson. Feel free to skip back through the video and re-watch anything you feel unsure about. We've now completed Lesson 1,